So I'm going to go through an example of how to use the approximation method and then compare it to not approximating and just actually finding the integral. Okay, and when we're approximating the area under the curve, we're actually going to use a definite integral to find the real answer because we have defined boundaries and we actually have a captured area. All right, so let's just go through an example, and I have the math kind of done out ahead so that this question doesn't take me a super long time with the tediousness of some of the mental math. All right, here we go. So using the left rectangular approximation method, that's what that stands for, find the approximate area under the curve x squared plus 2x plus 1 from x equals 0 to x equals 1 using 5 rectangles. So the more rectangles we use, the better the approximation. Okay, that should make sense to you. All right, so we're going to go from 0 up to 1. So maybe let's just stretch this out a little. Oh, sorry. Having a hard time writing on this. Up to 1. And then we're going to divide this up into 5 rectangles. And I did that already. 1, 2, 3, 4, 5. There we go. So this will be 1/5, 2/5, 3/5, 4/5, and 5/5. Okay, so we're finding the area trapped in here. And we're doing that by dividing it up into 5 rectangles. So it's pretty easy to see like the width of the rectangle. The height is what makes the difference with this left. So I have a rectangle here, and when I go to make the top of it, I'm going to go to the left and where it hits the graph and cut over and make the top. As opposed to, if I went to the right, I would make the top of the rectangle starting from the right. Okay, so I'm hoping that makes sense. So we're going to do the left, so we go to the left. I'm just going to color these in so you can see them. To the left, and that makes the top of the rectangle. Go to the left, and that makes the top. And go to the left, and then that cuts across and makes the top. So again, the left is what's hitting the graph, the left side of the interval. Okay, and then there's my 5 rectangles. And now I'm going to find the sum of all of those rectangles. So let's be super obvious here. This is 1, 2, 3, 4, 5. So I have 5 rectangles, and I'm going to find the sum of the areas of the rectangles. Okay, so we're not even being very mathy here, but this sign is this is a sum sign for a finite amount of objects. So in this case, 5 rectangles. So this is going to be equal area 1 plus area 2 plus area 3 plus area 4 plus area 5. Okay, now let's just look at how we get that area, how we get those areas. So area 1, the width of it is 1/5 because I took the interval 0 to 1 and divided it up into 5 rectangles. And then the height of it is the left of the interval, which is 0. Evaluate it in the function. So this is really f of 0. That will give me, f of 0 will give me the y value, which is the height, plus 1/5, and then this left of the second interval, go up till I hit the graph, it's the same as putting 1/5 in to the function and getting the height or the y value. Plus 1/5 times f of, now I'm at 2/5, plus 1/5 f of 3/5, right there, and plus 1/5 f of this one, which is 4/5, and I never make it to 1 because I'm using the left of every interval, so I used 0 up to 4/5. Okay, so now I'm actually going to plug those into the function to find the y values. So I have equals 1/5 times, if I put 0 into there, I get 0 squared plus 2 times 0 plus 1, so 1, plus 1/5. And if I put 1/5 in, so this is what I was telling you how I figured these all out ahead of time. So I get 36 over 25 plus 1/5, and then I get 49 over 25, and then plus 1/5, and then if I put 3/5 into x squared plus 2x plus 1, I get 64 over 25, and then if I put 4/5 in, I get 81 over 25. Okay, so you could, just letting you know what I did here. So I said f of 0 equals 0 squared plus 2 times 0 plus 1, which equals 1. And then I said f of 1/5 equals 1/5 squared plus 2 times 1/5 plus 1, which equaled 36 over 25. Okay, and then when I add that all up, I get, well, I found it as a decimal, so I'll just maybe tell you as the decimal, 2.04. Okay, so it's saying that the approximate area under that curve is 2.04. And you can see, I know that's going to be an under approximation because look, see all these pieces that I'm missing? So this is going to be a little less than the real answer. Does that make sense? Okay, so then I put this into the GeoGebra site here so you could compare. So again, I put the function in right here. I started at 0, I ended at 1, I had 5 rectangles, and I moved it all the way over for the left, and you can see the picture like what I drew, and see how the left of each rectangle is hitting the graph instead of the right, and then there's the area of 2.04. Okay, so hopefully that helped. This is an approximation. It's saying you can approximate area, and it's using our whole concept that we looked at the beginning of calculus of a limit, that if I let the width of every rectangle approach 0, then what I'm really saying is I have a lot of rectangles, and a lot of rectangles are going to add up to the right thing. So what's happening here is you have the sum of f of x times, let's just look at it here, times the change in x. So this was 1/5, and this was, you know, the height or the y value. And then what we're saying is if we take the change in x and we approach 0, then that's going to have this is going to turn into the sum of not 5 things now, but of an infinite amount of things. And if this is so small that it's 0, it just becomes the change in x, a little tiny change in x, which we call dx. So this sum sign is the sum of an infinite amount of things. And in this case, it's y values times really small x's. So it's the sum of a whole bunch of really, really small rectangles. Okay, so let's actually use that notation. to find the real answer. So we have 0 to 1, and we have x squared plus 2x plus 1 dx. Now, how we solve this is we find the antiderivative, and we do that using our 5 rules. So x cubed over 3 plus 2x squared over 2 plus x plus c, and we put that in big square brackets from 0 to 1 because it's a definite integral. And then we use the fundamental theorem of calculus, which says put a 1 in there. And then put a 0 in there. So it would have helped if I simplified that. Okay, and then those c's are going to cancel, and that all goes to 0. And I get 1/3 plus 2, which is going to be, I can make that 3 times 3, so 7 over 3. And 7 divided by 3, sorry, don't have a calculator here, but it should give us a little bit more. Sorry, trying to find my calculator. It should give us a little bit more than 2.04, and it does. It's, oh my goodness, I could have just said 2 plus 1/3, 2.33. Did not need a calculator for that. Okay, and then I don't even have to say approximately equal if I do this. Okay, so our approximation was an under approximation. Okay. And I'll just label the steps here. So this is a definite integral. And this is the antiderivative. And this is the fundamental theorem of calculus part. And then this is the area. We don't say it's area unless we're asked. Like, this is also just the answer to mathematically to that question, but it could represent area. All right, well, hopefully this helped clear up